So the topic for today is mirrors. Mirrors. I think we're doing all mirrors today, right? I don't think I'm doing anything. I don't think I'm doing anything that's not a mirror today. Let me just double check that. What's today? 23rd. Got any lenses in here? I don't think so. Nope, it's all mirrors. Two types of mirrors we're going to talk about today. Concave mirrors and convex mirrors. When we describe a mirror as being concave, that means the edges curve out toward the light source. Okay, so as you look at the mirror, it's going to open up toward you. That's the way I like to say it. And so when we do this, we have our mirrored surface here, and we have what's called the optical axis. The optical axis passes right through the center of that mirror, creates a mirror image, symmetric. And one of the things you're seeing in this is that we have these parallel rays coming in. And the nature of a spherical mirror, not just a mirror, talking about spherical mirrors, meaning there is a location somewhere on the optical axis that is the radius of curvature. And that point on the optical axis, which you'll see a little bit later on here, has the mirror surface all at the same distance. Okay. And what's happening here is we have parallel rays coming in. They reflect off the mirror surface, if it's spherical, and they all come back down to a point. That's if the rays are parallel, by the way. And that point is what we call our focal point. And that's going to be a very important aspect of doing these problems. Okay. So let's look at an example of this. Uh-oh. So, as we've talked about with our ray model, when we have an object, every single part of the object is going to either emit or reflect rays of light, which when we're trying to determine how that's being formed, it can look very cluttered. So in this example here, we're just considering the top of the object. Clearly, the bottom of the object, the light is going to reflect off and really just come right back. And so we expect the bottom of the object to end up on the optical axis as well. So we choose the top of the object as our point of interest here. Because if you got the bottom and you got the bottom's simple, right? The bottom's on the optical axis. There's no way it's off the optical axis unless you act unless you take the object and you actually move it or something. But we're never going to do that. So we really take the top, okay, the top. And the idea is that when this light reflects off of here, and it comes down, it's going to cross at a location. When all those rays cross, and it's not at the focal point, because this object is not at infinity. If it was, it would be at the focal point, but it's not here. So all those rays that come in, they reflect off the surface, and they all cross at a location. And that informs us that we've created an image. That's how you make images. Okay? Light comes from a point and has to return to a point, and that's how you recreate images. Well, you create an image, not recreate an image, right? And so our interest is choosing special rays that have very important properties for how they reflect in order to determine this intersection. That's our goal, okay? And we call these special rays because we can draw a lot of rays, but there's certain ones that just really work well. And there are rules for this. We'll cover those rules later. Like in this example here, we have a ray that's parallel to the optical axis. It reflects off and it goes through the focal point here, and then it comes down. We have another ray that hits on the optical axis on the mirror, and due to the law of reflection, has the same angle coming out. That also crosses through there. We got another ray down here that goes through the focal length, then it hits the mirror, then it goes parallel, and that crosses there. And there's a fourth ray, actually, that we're going to look at, and I'll keep you in suspense for that. Now, notice what you see here when it says mirror plane, and there's another line here. We make a very slight assumption when we create our equations. And that assumption is that this curvature is mild compared to the distances involved, and allows us to create equations that are technically approximations, but they're quite good approximations. And so when you see this and it's going through here, it's like, what's going on? It's because the equations we're going to use require that. That's like a little miscellaneous footnote that you never need to remember again. I'll just say that. It's not something you have to keep in mind always. It's just, it's a thing, and just know it's a thing. And so, all right. So we have a lot of different standards that we're going to work with here. Now, for the concave mirror that we see here, we have our point of interest, right? And we have our curvature here, okay? So right here are, well, the point C here is the center of curvature. That's what it's determined by the radius. So every single point on the mirror here is equal distance from the point of curvature, the center of curvature here. And in this situation here, we speak of the distance from the radius of curvature. We speak of the distance of the radius of curvature as being positive. Positive if you have a concave surface. This is negative here if you have a convex surface. So if your radius of curvature is on the other side as your object, that's a negative value. So, okay, so this is positive for concave. We're on base. Well, your image and your point are on the same side, right? It's radius of curvature and point on the same side, and same thing over here. S is how we're going to indicate our object distance. If we're on the same side as our point, positive. Same thing with S prime. S prime represents the image distance. Also positive if you're on the same side. So we're going to deal with concave stuff first, and everything's positive there. Okay, object distance, image distance, and the radius of curvature are all positive. So we'll keep that in mind for now. We'll worry about the convex stuff a little bit later in the class. All right, so here is our relationship here. So what we have is this. We have our point of interest, which we'll call him P here. We have our radius of curvature, right here, C. And we are interested in determining where our image distance is going to be. So in this particular example here, we have a light. We're just choosing one particular light ray to do this. In fact, actually, we chose two light rays. And we chose one that comes up and hits that point B, reflects off. We follow the law of reflection here. And it goes through the optical axis at this location here. We also are choosing an array that comes back, that comes right along the optical axis, comes through. So those two lines intersect there. That's where our image is located. Now let's watch this here. If we look at the triangle, okay, so we're going to talk about triangle here. Oh, got to wear my cool Michael Jackson glove first, because that's what my drawing tablet wants me to do. How do you put this on? I can't remember now. Here it is. So look at the triangle PBC. So let me actually do that a little differently here. So triangle PBC has the following relationship. Alpha is the angle that ray makes with the optical axis. We have theta is our angle of reflection, and that's going to equal phi right here. And that's just a property of triangles, is that the two angles that are opposite of the supplement here is going to be equal to this angle that's out here. And you can see that because if you add up, right, this is alpha plus theta plus 180 minus phi, but then the 180s drop out and you end up having this relationship here. Okay, so that doesn't need to be there right now. All right, so there's that. So we have that first. If we also look at triangle, excuse me, triangle P prime, B, and C. Okay, that triangle. And what we're going to end up with there, excuse me, make sure I got that right. Yeah, beta. Phi. Yeah, so this is the same thing here. Our phi plus our theta up here is a bit, according to the same relationship, that's also equal to beta. When you combine these equations together, because you got these thetas here and you got these phis here, if you add all this up, you end up getting that alpha plus beta is 2 theta. Okay. Oh, it's phi? Oh, that's why it's phi, not theta. I was like, what is going on? So that's phi. So that works, right? Yes, if I subtract the, okay, that works. Okay, so alpha plus beta equals 2 phi. All right, so that's this. So alpha, beta, 2 phi there. Okay, great. Now, this is what I was talking about in terms of an approximation. If you look here, the tangent, okay, oh my goodness. Oh my goodness. All right, the tangent of alpha is approximately h divided by s. S is this distance down here, which is from the point of interest, our object, to the plane mirror, right here. Okay, so there's a little delta here. This is what I was talking about before, how we make this approximation that this delta goes to 0, and that we're sufficiently far away that this curvature is not like a substantial thing. Because if you incorporate this, there's a little bit of an offset, but we approximate tangent of alpha as being h over s. And then what we could also do is, because the angle is very small, tangent alpha is really just alpha. That's true for sine functions and for tangents. When your angle is sufficiently small, and your angle can be as large as 20 degrees actually, and this approximation pretty much holds. So the alpha is equal to h over s. You can do a similar argument with beta. Beta is approximately h over s prime. That's where the image distance is. And phi is approximately, what would that be here? h over r, the radius of curvature. And so if I plug all of these in to this equation right here, it goes up in here, and divide out all the h's, we end up with this nice little equation right down here. I just drew over it. Brilliant. Anyway, we get this equation down here, which represents our mirror equation. Spherical mirrors follow this, right? So that's how we derive this thing here. So we got to remember this quantity here. It looks strange. The math is kind of weird here. All right. Now, if we do consider an object that is extremely far away, okay, so let me write the equation down again down here. 1 over s, 1 over s prime, and 2 over r. Now, if we consider a source of light that is extremely far away, so far away that we can consider this term here to be 0, then this relationship turns into this thing right here, where our image distance becomes r over 2. Okay? Combine that with the definition of what focal length is, where, that's what the definition of focal length is. When rays come in parallel, they all reflect off the mirror and they come down to a point which is the focal point. If you're closer, that gets pushed further out, but that is where rays that are parallel come. And so we can see the relationship between that where that image is formed is exactly half of the radius, because the radius is from here to here, and our s prime is exactly half that value. So the focal length is it can be replaced in the equation. So the equation can be, I'll write over here again, 1 over s prime equals 1 over f, where f's the focal length. That's another way we can write that equation, and it just sort of depends on what information you're given. But you know, this relationship you see down here is pretty much solid. That's exactly what, that's always true in these mirrors. Okay. So, the reverse is true as well. If you have an object that's actually at your focal point, then you can't form images with it. Because what happens is the light will reflect off the mirror and go parallel. And so the image never gets formed. It just looks sort of blurry. You'll see this too if you ever, I mean, curved mirrors are not the most common thing, but like I have this makeup mirror, not for myself, but and it's curved. The same thing is as you approach it, you sort of see your face, and then you get too close to it, everything just kind of blurs away. And then if you get really close to it, everything kind of flips around. And so we'll look at examples of that. I don't know if we do that today, but we'll look at examples of that. But in this particular case here, an image can't be formed, and that's just the opposite principle there. All right, so this is the good stuff right here. This is the slide you got to really pay attention to. That is our mirror equation. We derive this for a concave mirror, but guess what? It works for convex as well. And I'm not going to go through that particular derivation, but your textbook does. And it's pretty much the same thing. You're forming triangles, you make approximations with your trig functions, you get the exact same relationship. What you got to remember though down here is the following. When it comes to R or F, concave toward the object is positive, convex towards the object is negative. Okay? Your S, which is the object distance, well, you're always going to have your object on, you know, the same side of the mirror as the curvature for the concave. So it's S is always positive. That's just, but S prime can be negative. If S prime is positive, then that means the image is formed on the same side as where the object is, and it is a real image. And if you remember, we've talked a lot about virtual and real images. What that means is this: when we say an object is a real image, that means light rays actually reach that location. They don't, because sometimes they can just appear to come from that location. That's what virtual images are. A virtual image is an image that's formed where light appears to come from that spot, but doesn't actually come from the spot. And plane mirrors always produce virtual images. The image always appears like it's on the other side, not on the same side as you. And that's when S prime becomes negative. Okay. And so this is the convention. Now, let me warn you about this though. This is the convention for our mirrors, concave and convex. Okay. What's a little tricky is next week we're going to look at lenses, and we're going to look at other types of refractive surfaces. And there's equations and conventions just like this, but they're subtly different. Sometimes we call some things positive, some things negative. That's different from here. But you want to really, print the slide out, stick it in your pocket, pull it out occasionally, look at it, shake your head like, yeah, I got this, put it back, take it out another half an hour for now. But anyway, you'll see this again next class when we do our lenses, and then we do our refractive surfaces and things like that. But this is what we're doing for now. All right. So now, what else about these objects? Well, these images here. What ends up happening is after the image is formed, it may or may not be magnified. So what we are doing here is you see a couple special rays here. One ray goes right through the optical axis and it obeys the law of refraction. Okay. This ray goes through the radius of curvature, and so when it hits perpendicular. And so the ray reflects exactly back. And so you can see where the image is formed. You only need two rays to do that here. But as you can see, and this stuff is drawn to scale, and if you draw this stuff to scale, you will get the correct dimensions for things. Well, I guess that's what for scale means. That's kind of redundant. Anyway, but if you look here, these triangles, okay, this triangle that's colored in, what was that, like peach or something? I don't know what that is. Looks like a peach to me. That's a strange color. Anyway, there's a triangle there, and there's a triangle underneath the optical axis, which is bluish. And those are similar triangles. Because the triangles are similar, these angles here, if you make a little ratio, like a ratio would be the object height here and the object distance, that ratio would also be equal to the ratio of the image distance to the image height. And so we have this relationship right here, which tells us what the magnification is. Oops, sorry. Go back there. So this tells us the magnification of the object. And so you can either have you can do a ratio of the heights here, or you could do a ratio of the distances. Notice there's a negative sign here. And the reason why the negative sign there is to communicate that the image is inverted. So when you do magnification, a number that's bigger than 1 is obviously an object that has been magnified to be larger. If the value for m is less, that's going to indicate that the object is going to look smaller. And if there is a negative sign, okay, that's going to indicate that the object is inverted. So when you work out these quantities here, be mindful of what the m means. You could say two things: larger, smaller, inverted or not. That's what you can do. All right, let's try a question. Let's do this question. You see an upright, magnified image of your face when you look into a magnifying cosmetic mirror. The image is located where? It's C. Okay, what's going on here? Well, let's go back. See this? If you have a mirror here, the image is inverted. That's normal. Okay, so if you have the spherical mirror here, and normally your image is inverted, but if you can see you have an upright magnified image of your face, then according to this, that S prime is negative. Okay, see what I'm saying here? This S prime is negative to cancel with that negative. S is always positive, by the way. But the S prime here is negative, so it cancels with that negative, and we end up with a upright image. So whatever we did here, we got to a position where the image was actually behind the mirror surface. That's a virtual image. And how do you get that? Well, again, we'll work on an example in a minute here. It's because you got too close. You got a little too close. If you get far enough away, things flip. But there's something interesting that happens when you cross the focal length. Things are different. All right. Oops. All right, let's do it. All right, so this example here, we have a concave mirror forms an image on a wall 3 meters in front of the mirror. Wait, a concave mirror forms an image on a wall 3 meters in front of the mirror. Oh, it's back here. Of a headlamp filament 10 centimeters in front of the mirror. Okay, so right here we have our filament, whatever. What's the radius of curvature in the focal length of the mirror if that's how the image got formed? What's the lateral magnification? What is the image height? All right, let's do it. Now, what we could see here is, now these are not special rays. Just want to be clear about that. What I've drawn here, I didn't draw this, but what this is drawn out here are not special rays. They're just some rays, just to give you a sense of how the image is formed. We're going to work out a technique where we can do this more easily, because this is more of just like it's not a guess, but what happens here is, though, each ray that hits obeys the law of reflection. So you can draw, what you do here is this. If you wanted to draw it like this, you have to get out a ruler or a straight edge or something, and at each location you want to have a ray, you have to draw a normal line. And then you have to draw a ray that hits it, measure the angle on the other side of the normal line to obey the law of reflection. So if you did that, you could produce this here, but that's a lot of work. That's a pain in the butt, let's be honest. We're not going to do it that way, but I just have this picture just because we're working out some numbers before we get into the ray tracing right now. Screen share is gone. All right, here we go. So, all right, so what are we told here? Well, how do we attach these numbers, right, to quantities in our equation here? So the 3 meters in front of the mirror, that is the image distance. That's your S prime. The actual object was placed 10 centimeters in front of the mirror. That's 0.1. Okay, so I have my S and my S prime. To get the radius to curvature, we use that equation that we have. So what I did is this. I'll write that equation down once again because you don't see it here actually. So that equation is 1 over S plus 1 over S prime equals 2 over R. And what I did here is I rearranged the equation algebraically, and I solve for R, which then you get this relationship here, and the radius to curvature apparently comes out to be 0.194. And we divide that in half, and we get our focal length to be 0.0968. So our image is just a tad outside of the focal length, which explains why it's so far away. It is extremely far away because guess what? If we were to get a little bit closer to that focal length, that image goes to infinity and we don't actually have an image. So when we creep real close to that focal length, that's what happens here. So now that we have radius to curvature, we have a focal length, we now want to know what the lateral magnification is. So we can take a ratio of our S prime to S, and S prime to S is minus 30. That is the ratio. So what that means is this. It's 30 times larger than the object. That's the image. The image is 30 times larger than the object, and it is flipped. It's inverted. Okay. Now, what will the image height be if the object height is 5 millimeters? So what we do is we take the exact same relationship that you see here. So the M is equal to the ratio of S prime to S. Well, it's also equal to Y prime to Y. And so we're going to solve for our Y prime here. We know that the object is 5 millimeters. And so this is going to get magnified by 30, right? And so we get our distance here, our new height to be 15 centimeters. So it's 30 times larger. The negative here still indicates that it is flipped. It is flipped, okay? So also one thing about this problem that was a deviation from what we're normally going to do. Normally we take this object and we move it so that the bottom lies on the optical axis. And if we did that, then this would shift down, and then this would be on the optical axis. Well, you don't have to do that. When we start drawing these special rays, you're going to want to do that. Okay. So any questions about this problem, or is this kind of okay? Kind of okay. That's what I said. Kind of okay. All right. Let's then get back to something. Let's tell my screen share to get with it here. Oh, well, here we go. Here is our graphical methods here. Okay. So, now, you need to, in order to figure out where your image is located, all right, you have to draw rays and look for an intersection. Now, at an absolute minimum, you can get away with 2 rays. You can get away with 2 rays. However, there are 4 special rays that could be drawn. And that gives you some flexibility there, because in some situations it's easier to draw one ray compared to another ray. And in some situations you can't draw rays. Okay? In some cases you won't be able to draw any rays at all, actually. So let's look at what these rays are. Ray number 1. Now, again, the way we're doing this is we're placing our object so that the base of it is on the optical axis, and we are considering what the top of the object is doing. Because that automatically would kind of fill in everything else that we need. Ray number 1 runs parallel to the optical axis. It reflects off and it goes through the focal length. All right? That's ray 1. Ray number 2 first goes through the focal point, then it reflects off and goes parallel. So ray 1 and 2 are very similar rays. One is parallel, reflects, goes through the focal length. The other one does the opposite. Goes through the focal length first, then reflects and goes parallel. Okay, and you can see they intersect right here at this point Q prime. We have a couple other ones we can do. If you pass a ray through the radius of curvature, you hit the mirror perpendicularly. Perpendicularly? I'm going to go with it. And it gets reflected directly back. Okay, and that's another ray. A fourth ray goes from our object, hits at the optical axis on the mirror, and then heads down as well. So what happens here is this ray 4 just obeys the optic, obeys the, well, they all obey the law of reflection, but it's more obvious how that's done here because you have an angle here and an angle here that was obeyed. So, like I said, you can draw all 4. You can get away with 2. Some are hard to do, though. For example, let's say we placed our object on the radius of curvature. Well, you kind of can't draw a line that goes from the top of it through C and then hits your mirror, because it's going to go like straight down. So some rays just don't work. So you got to choose the ones that do work. All right, example 2. Here we go. Uh-oh. So we have a 3 centimeter high object located 20 centimeters from a concave mirror. The mirror's radius of curvature is 80 centimeters. We want to determine the position, orientation, and image and height of the image. Now, okay, so let's be very clear what we're talking about here. I'm going to do this in a couple different ways. I'm going to show you the ray tracing first. Okay? You don't have to do the ray tracing unless I tell you to do the ray tracing. Then you got to do the ray tracing. But the ray tracing sort of helps visualize what's going on here, and it acts as sort of a sanity check. When you get a result, if you try to quickly sketch out to scale how things look, you'll get a decent idea if your answer is right or not. Now, here's something that's unique about this problem, though. Our object is located 20 centimeters from the mirror. We are within the focal length. Focal length is 40 here, right? So we're within that. And this is sort of that problem, that first question I asked you. Okay, when you get close enough to the mirror, you end up seeing an upright image, but it's a virtual image. So how do we know that? Okay, we're going to do 3 rays here. Okay, now, when you're within the focal length, this is going to work a little bit different here. That first ray, okay, what happens is we don't have a ray that really goes through the focal length. So I'm going to start at my focal length. I draw a little dashed line. Then we hit our object. Then we reflect off, and the ray goes parallel. That was one of, right? That was what we call ray 2, right? That was ray 2. Ray 1 is when the ray goes parallel first, hits the mirror, then goes to the focal length. So when we're within the focal length here, you got to be a little bit careful about what's happening, because the second ray has to be drawn from the focal length, which means we have to sort of do a little imaginary line before we get to our object. The second ray that we're going to do is the one that hits the optical axis and comes down. So you see here, though, we got something funny when we draw that stuff. This ray goes this way, this ray goes this way, this ray goes this way. The other ray was a radius of curvature ray. Now, that would be way over here. Like, it would come in like, if I had to draw it, it would be something crazy like be way back here, and it would come in like, no. Oh my goodness. What? I'm still trying to figure out this drawing path. I don't understand sometimes. Just doesn't want to draw now. Oh, here we go. Now it will draw. Oh, wait, because I can't draw out there? Is that why? Oh my goodness. It would come like this. It'd come way over here. Not my day. All right. Anyway, there's a radius curvature one we can draw. I can't do it though. Something like that. It looks terrible. Anyway, okay, never mind. All right, so what we'll notice in here is that these rays diverge. They diverge. We're never going to form an image over here, but they do converge somewhere. They converge on the other side. So what we do is we look at the rays that come out and we trace backwards. This ray traced backwards is going to intersect up here. This ray is traced backwards is going to intersect there. So there is an intersection point, but not on the side of the mirror. The left side is on the right side. So if you draw out your ray stuff here and you notice that your lines are divergent, something's up. We got a virtual image now. Now, by the way, this will always be true. If you're within the focal length, you always end up with a virtual image. Always. Okay, so that's just something to know. All right, so according to this, looks like we're going to end up with a virtual image that's bigger. Right? So let's do the math now. Let's do the math. All right, I'm going to zoom in a bit here. I actually redrew this. The ray tracing, I'll be honest, is kind of a pain. It's a little difficult to do, but I redrew it here. I don't know why I redrew it since I already had a diagram for it, but anyway, I have my 3 rays there. So this is ray 1, 2, and 4. That's what I did. All right, so let's actually see what's going on here. Let me zoom back out a bit. All right, so my numbers here. I have a 3 centimeter high object. That's our Y value. It's located 20 centimeters from a concave mirror. That's S. Radius of curvature is 80, which means F is 40. So I use my equation, the equation that, I don't have it written here for some reason, but it's the same equation that we always have. So it'll be 1 over 20 plus S prime, 1 over S prime, and 1 over 40. And we'll do 1 over F. And you solve this and you end up getting a negative 40 when you do this. Now it's negative. That means it's a virtual image. So it's going to be 40 centimeters on this side of it. We work out the magnification. The negative 40 cancels with this negative, and we see that our image is actually twice as large, right? And that means it's going to look 6 centimeters tall. Okay, so I had to do the ray trace, and you can see pretty close to being exactly double. It's very hard to draw these things accurately, though. Okay, fantastic. 3 is hard to draw. Yes, it is. Yes. So this is going to be cool. What we're going to do is we're going to take our concave mirror and we're going to look at basically 4 different examples. Okay, 4 different examples of the images that can be formed. And these 4 examples basically encompass everything that you could do. We're going to have an object that is significantly distant from the mirror. We're going to be at the radius of curvature, we're going to be at the focal length, and then we're going to be within the focal length. And those are really the 4 different scenarios that exist. So let's do this one here. The image that you see down here is just sort of your random, I'm beyond the radius of curvature. So we have 30 centimeters here, but honestly, this could be anything that's beyond 20. Okay, and as you see our rays here, we had our first one that runs parallel, goes to focal length. Second ray goes to focal length, then goes parallel. Third ray goes to radius of curvature. Fourth ray hits the optical axis. And so we can see our image is formed here. It's formed between the radius of curvature and the focal length. Right? When we are actually on the radius of curvature, then ray 3 can't really do, right? Because it goes through C and we're standing on C. But we can do 1 and we can do 2, we can do 4. And what we get is something interesting, is that the image is formed at the exact same location and it's flipped and it's the exact same size. So that's kind of neat. And I'll work out the numbers here. I just want to show you the pictures first. Now, for at the focal length, you got some funky stuff going on here. I could draw away ray 1 just fine. Through the focal, parallel, then through the focal length and away. Great. I can't draw ray 2. Right? Ray 2 requires me to first go through the focal length, then reflect off the mirror. Can't do that. So that's out. 3 is going to hit the mirror, come right back, and go through the radius of curvature. And then 4 is going to hit the optical axis. Now, if things are drawn out correctly, you notice something kind of funny here. These rays are parallel, right? So, but that's the definition of the focal length. Okay, anything at the focal length, when it bounces off the mirror, the rays are going to go parallel. Well, these rays are parallel. It means you're not going to form an image. You won't see anything. It'll just look blurry or distorted or whatever, but you won't be able to form an image. All right. And then here's when you are within the focal length. This is very similar to the example we just did. You can draw those rays out, but you're going to have to trace back to figure out where the image is. And ray 2 is a little tricky because you have to first go to the focal length, which means we have to kind of back trace it, and then we hit it and go through. So let's look at the numbers behind this stuff now. All right. So what we have here is our object distance is at 30. When we solve the equation, now the equation, I'm not going to rewrite it, but just so you know, all these s primes that I'm putting down here, just use the equation to figure it out. So I get 15 centimeters. It's a real image. It's positive. And it's smaller and inverted. So I got my m value to be minus 1/2. And what happens here is, as you push this s further back, this value for s, if I go further away, what happens is the, this gets really, really big. And what happens is the image gets pushed closer and closer to the focal length, and it gets smaller and smaller and smaller. Okay, because you have the s on the bottom here. And so you're going to end up with a ratio that's very, very small. For the being at the radius of curvature, you end up with the same distance. So if you put in 20, you get 20 back. And we see that we're at minus 1 here. So that means same size and flipped. Real image, same size, flipped. Okay, let's go to the next examples. All right, if you attempt to solve for s prime here, you won't get anything. You'll divide by 0. And so I don't recommend you do that. So no image forms, end of story. If we solve for 5 centimeters, we get a minus 10, so we have a virtual image. The magnification is a +2, so it's a larger and an erect image. And what happens here is as you get closer and closer, this gets closer and closer to the focal length. This thing gets farther and farther away, and it gets bigger and bigger and bigger as well. So yeah, because you're basically your s prime. Sorry, your s starts to approach f, right? And so you end up with this s prime being really huge. Let me think here. Okay, yeah, that's all the examples. That's all these examples here. So let's do, I think I have another example right off the bat now, though. Yeah, okay, so here we go. Here's another example here. We have an object 0.6 centimeters tall, that's y, is placed 16.5 centimeters to the left of the vertex of a concave spherical mirror, that's s. Having a radius of curvature of 22. All right, that's r. So we got all our numbers here. We want to draw a principal ray diagram showing the formation of the image. All right, so I have already done that here. So let me zoom in a little bit because it's a little faint. Now I tried to draw this out as much to scale as I possibly can. So the distance here, the object distance, which is at 16.5, is to scale to the radius of curvature here. And then I drew the focal length, which is half that. So I got my rays here. I got my parallel one. So it's kind of hard to see that. I'll annotate this so you can see it. But I got a parallel ray right here. Hits goes through focal length. Ray 2 first goes through focal length, So it comes down like this. Then it reflects off, goes parallel. So those two already, you can see how the intersection is going to end up over here. And 3 is going to go through the radius of curvature, so I'm going to hit and come back, and I go through the radius of curvature. You just draw a line that just connects those 2 points there. And then ray 4 obviously hits the optical axis, goes down there. So you can see, did a pretty decent job. It didn't perfectly intersect. Why? Because, I don't know, maybe I didn't draw the curvature right here. Maybe I didn't get, like, if you can see here, like, ray 4 is messed up, right? I mean, you can see what I did here. I drew this line, and then my next line looks like this. And that's not really obeying the law of reflection too well. I mean, it's close. It's not perfect. And so that line there dips a little lower than it's supposed to. Anyway, it was hard. It was hard to do that. It's a little challenging. Anyway, let's do the equations here. If I put into the mirror equation, I get a 33 centimeter real image. So that makes sense. I'm farther away than I thought I would be. Good. You know, by the way, if you're in between the radius of curvature and the focal length, everything gets kind of inverted in the sense that if we are far away, your image gets formed within this area, but if you're in this area, the image gets formed farther away. And as you creep towards the focal length, everything gets farther and farther and farther away. Same thing too, everything gets farther away when you're on this side too. All right, anyway. I work out my magnification, I get a -2. So the object is a real image, it's twice as large, and it's inverted. And that is true. So, any questions about that? That's weird. Yeah. So, now notice the consistency in these problems, right? The ray tracing is always done the same way. The equations are pretty simple. You got to remember the sign conventions. That's really it. You got to remember what's positive, what's negative, things like that. I drew a ray diagram. So I like to look at that one first. Oops, sorry. Well, this came out really faint, didn't it? Oh my goodness. All right, so what are we doing here? Spherical concave mirror, got it. Radius curvature 32. Okay, so 32 is R, right? Great. F is half that, 16. Yep. 3 centimeter tall object, that's why. All right. With optical axis, we are 12 centimeters from the left of the vertex, so we are going to get our virtual image here because we're within 16. So let's go through the math first, I suppose. You solve for your S prime, you get a -48. Minus means virtual image, we're on the other side of the mirror. And quite far away, actually, right? Magnification here is going to put in our values for S prime and S. We get a +4, so we have a larger erect image, 4 times larger actually, and so that means we're going to have a 12 centimeter tall image. Great, let's do the ray tracing. We don't have to do it here, I just did it. So I'm going to annotate this because the scan didn't come up so nicely here. So the first ray is one that goes parallel, and then it goes through the focal length. So that's going to be this one here and down to there. Fantastic. The second one, well, again, the way this works for the second one is I'm already within the focal length, so I have a little line here. It's a line goes from here up to here, and I didn't show it, but it heads over this way. I guess I didn't show that way. Then I did ray 3, which is, hits our mirror, then goes backwards to the radius of curvature. And then I have that fourth one, which I opted not to do, and that's the one that goes through the vertex here. So it's boom, and then it would go down like that. And if I trace that back, you can see I still get up to here as well. So I trace all these back, right? And I end up with this thing here. And that makes sense. It works. Much further away, much taller. Everything seems to make sense with the numbers there, so that's pretty straightforward. All right, fantastic. Let's keep going. Convex, yeah. Convex. All right. So convex mirror is one that curves away from the source. That means our optical axis and our radius, well, the optical axis is still the same, but the radius of curvature now is negative. because anything on the right side of the mirror, according to the picture here, is negative. So our images, if they're over here, they're negative, and any distance is negative. So that means the radius of curvature would actually be negative in this case here. All right, and in all these cases here, you know, the focal length's also back here. If you have parallel rays come in, then they're going to diverge away, right? And so you got to trace back to find your focal length there. So, you know, these look different. They may seem strange, but nothing is actually different here. Okay, so here's I don't know what the heck this thing is. This is I don't know where I got this from actually, but you can see our ray tracing here. We get a virtual image. We got to trace back through the stuff here. So you can see in the image here, this is a virtual image. It appears as if this stuff is further back from the surface. And things look pretty small. That's a very common thing when you have these. So now I'm not going to go through the same derivation as before. You can though. I don't have the figure with me here, but it's the same thing. You have an alpha, which is an angle from the object. You have your beta, which is an angle that's formed from the image. So that it would be over here. Then you have your phi, which is the reflective angle here. And you can work out the same things, but what you find is that you get the exact same equation. Nothing's different for the convex mirror except for r is negative. R is negative. And that's really the only thing you need to be mindful of here, is making sure r is negative and then just properly interpret the mathematics that you get. Okay. All right. Same stuff. Focal points, no difference there. Don't need to say much about that. Let's just jump right into it then. So very similar problem to the first thing I started. This is just for the purposes of you know, these aren't special rays or anything. Well, they kind of are. Well, they actually are special rays. Never mind. But what we have here is we have a person. It looks like their reflection in a convex mirror. That's going to be the person. They're 1.6 meters tall, apparently. And that's your y value. And we are 75 centimeters away from the surface. So that's S. Radius of curvature is a negative, right? 7.2 centimeters. So the focal length is negative as well. Let's go look at how this is done. All right, so, okay. All right, so I got my numbers in here. This is the other problem. What am I doing? All right. Okay, so yeah, when I raise the curvature, negative 7.2. Distance, object distance, 75 centimeters. I'm using that equation, I rearranged it here, and I get a negative 3.4 centimeters. So it is a virtual image. It is just barely behind, actually, the mirror. Barely behind. Now, I'm pretty far away, honestly, though. So let me think about this. I'm pretty far away. And so what is the focal length here? The focal length is half this. So half of 72 is 36, right? Oh, I'm close. Look how close I am. Very, very close to the focal length. If I move this further back, this would inch closer to 3.6, actually. So this makes a ton of sense. We end up with a pretty small image because, look, if you look at your magnification ratio here, it's S prime to S, and your S is a big number. So we end up with a pretty small object. It's only 4.6% the original size, so it's only 7.3 centimeters here. So let's interpret everything. We get a negative value for S. It's a virtual image behind the mirror. The object will look smaller, and because the magnification is positive, it is an upright image. So if you have this setup here, that's what you're going to see in that mirror. So that's cool. That's cool. All right, so here's the ray tracing for the mirrors. Now, this is not different, really. I mean, we actually have the same rays, but because we have a lot of virtual images, it's going to look funny. So let's go through them. Ray number 1, as always, goes parallel, reflects off. But when it reflects off, you can trace backwards to the focal length. So you draw the parallel ray, you go from your focal length up to where it hits, and you can draw your ray going out. That's one. The second ray is the one where you first go through the focal length, which we can't do. So I'm going to draw, what I do here is we draw a line. So we draw this line here. Okay, and then wherever we cross, we draw a line to my focal length. Wherever we cross the mirror, that's where you can draw your ray going out. Okay. 3 is through the radius of curvature. You just draw a straight line that goes from your object all the way to C. Easy enough because it reflects directly off. And then you also have your vertex, the optical axis one. And again, we have to trace that back. So because it's a virtual image, all these have to be traced back, and that's how we end up forming things. So it's the same principal rays, but because it's a virtual image, you have to trace the lines back because the light doesn't actually come from that area. So what do we got here? Let's go through it. 0.6 centimeter tall object, that's Y. Yeah, that's Y. This is your S, 16.5. Radius of curvature is 22. That means F is 11. Let's do our principal ray diagram. Okay, I did that here. So I attempted to draw this to scale. I did not draw this to scale at all, though, right? Did I? No way. 0.6 centimeter tall object. Huh? Is this right? What was I thinking when I drew it? It's totally not right at all. Okay, this object is oddly large. Okay, I don't know why I did that, but this should be way tinier. I mean, it's going to be to scale with the image. It's just not to scale with the optical axis information on here. I don't know why I made it so huge, though. Anyway, the distances on the optical axis are to scale, but the heights are just messed up. I don't know. I mean, we still do this, but... All right, let's draw ray 1. We go parallel. We hit. Where we hit, we trace down to the focal length. Okay, I mean, the ray, obviously goes out like this, but we're looking for the intersection, so I'm just tracing back to get to F. Number 2, hit. Now, again, what I'm doing here, what you can't see, is I drew a line to make sure that we reach F, and then I reflect that away, and I trace that back to get to there. Okay. And then number 3 is through the radius of curvature. So again, I have to draw a line that goes right over to here, and we see where the intersection is. Right? We see the intersection right there. So even though I didn't draw the height to scale, let me put it this way, my x-axis is to scale. It's just not to scale with the y-axis. But it's fine, you can have different scaling. I mean, if you've ever done a trig class, every single trig function, every time you see a graph of it, it's not the proper scale because it would look funny. Because it would be really, really short. Because a full period is what? It's 6.28 radians, and then the height is only 1, so it would look squished. So that's why you never really see them properly to scale. So I didn't scale Y here. But anyway, smaller. Let's go through the math though. So make sure you choose your radius curvature to be negative. Got it. I go ahead and plug in for S prime, and I get negative 6.6 centimeters, so virtual image, as expected. Not too far away, so I'm not too close to the focal length here. If I were to inch this further away, this creeps over here. If I were to move S a little further in, this actually creeps a little bit further back. Gets closer to the mirror. Magnification, positive 0.4, so it is a smaller erect image. Great. Virtual image, smaller, 40% smaller, and upright, Fantastic. We're through. Now, one thing that's really nice about this stuff, right? There is a consistency in all these problems. And with the consistency for all these problems, it makes this stuff not so bad.